All right, welcome everybody. My name is Kevin Hawkins. I'm the Developer Tools Lead at Qualcomm. And I want to talk to you about how to uncover your game's power and performance profile, why it's important, and what it means for your end user experience. So, if you don't know, as a developer, you want to focus your efforts on the platforms that have the largest market share. And Qualcomm Snapdragon processors are used in over 1 billion devices worldwide, including many of the flagship smartphones that are available today. This includes more than just the flagships, includes multiple tiers, so your low and mid tiers as well, especially those devices in developing markets. Obviously, smartphones, but also your tablets and watches and other wearables, as well as TV devices and the upcoming virtual reality devices. But with all that, we need to make sure that developers can develop good applications, good games, good user experiences for those devices. And we put a lot of effort into the developer tools to help you with that. So we look at every stage of the software development pipeline. And what we've done is develop tools for each of those segments. Starting with the left side, you have your kind of create phase, your SDKs. We have the Adreno SDK, which is a collection of samples and documentation about how to best use the Adreno Adreno GPU. We have the All Join and All Play, which are wireless SDKs. FastCV for computer vision. The Hexagon SDK, if you're interested in developing or offloading work to the DSP, this SDK will help you there. The LTE broadcast is for content distribution. We have this Mari SDK that's for heterogeneous computing, where you can develop code and it will automatically distribute workload across the system. And then we have the Vuforia, which is actually at our booth. If you're interested in augmented reality, that SDK is also available. And then, of course, compiler. If you develop any native code, we have an LLVM compiler to optimize for Snapdragon chipsets. We have debuggers that we released earlier this year for Eclipse and Visual Studio. Now, they allow for NDK debugging, but also for kernel OpenCL debugging as well, if you're interested in that. And of course, optimize. And the one thing that I'm going to talk to you a bit about today is Snapdragon Profiler, which is brand new. But we do have the Adreno Profiler, which is a GPU debugging analysis and profiler for the GPU. And Trepin Profiler, which is for power and other on-device performance. And finally, the deploy phase, which is all these development platforms that you can get from us. You do have the 1 billion plus Android devices that are commercially available now, but you also have mobile development platforms. We have Dragon boards, which are embedded developer kits, various single board computers, and the Internet of Things dev kits, which I believe are fairly new from Qualcomm. Important thing is that all of these things are available for download for free at developer.qualcomm.com, so you can get those today. So talk to you about Snapdragon Profiler a little bit. It is a heterogeneous system profiling tool. We just released this at the end of July, about a month and a half ago. And like I mentioned, it's a free download, developer.qualcomm.com. So you can profile the CPU, the GPU, your networking data, power, thermal, and a few other things. And we're going to continue to build on this system over time. We have what we call a plug-and-play experience. What we mean by that is that you can use commercial devices and commercial applications and connect directly over USB and Wi-Fi. You do not need to root your device or do any weird trickery with your device for it to work. We do have support for Windows and OS X. We have a new release coming out soon that'll have Linux as well. And it's something that any developer can use. So we have system developers, app developers, game developers, and other developers using Android devices with Snapdragon chipsets that are using this profiler to understand performance for their applications. And we do support all the different tiers of Snapdragon devices that I had mentioned before. So this is what it looks like, and I just kind of want to give an overview of it, and then we can show it later. But this is what we call our real-time view, and kind of makes sense. It's real time. So this is real-time data that's streaming from the device. And in this top section, is showing the system level metrics. So the bar graph there at the top is showing your CPU frequencies across the different CPU cores. So you can understand what level of frequency are each of the cores operating at and collectively as a system. The next four tracks are your CPU utilization. So this is again looking at the overall system, how much of the CPU is being utilized. And then the last one there, the line graph, would be the system memory. And then the next block below is looking at the application metrics in particular. So I can look at my app metrics and then understand the full system metrics and see what the correlation is and how my application might be impacting the system. But in this example, it's showing the frames per second and CPU utilization. And this particular application is, I believe, a CPU-bound application. Uses all the CPU cores pretty heavily. It's not necessarily heavy on the GPU, so this is typically what you would see. It's a fairly stable application as well. On the left-hand side, just to point out, on the top left is a list of all the user space processes. So you can select any of your processes and see what metrics, and the metrics list is below that on the left side, where you can see process and CPU, EGL, GPU, and so on. So as you select a process, whatever's available to gather data from that process will show up in that list. And as an example, this is a graphics application, so GPU metrics are available. But if you were to select, I don't know, the Play Store app or something, you would not see GPU metrics, just as a small example. Further below that would be all your system level metrics, which include power and thermal and networking and others. So the next mode we have is what we call trace, and I assume everybody's familiar with Android systrace or relatively familiar. What we're doing is building out something that takes all the same Android systrace data and adds more to it. So a lot of what you see here, the trace kernel section there at the top and the trace process 0, that's pretty much all the same stuff that you get out of the Android systrace tool. Hopefully we make it look a little better and operate a little bit better, but what we're really doing is that last block below called GPU stages, and that's where we think we can really provide some value to you as a developer. So all this stuff is correlated on the same timeline, and that GPU stages is actually showing you what's going on inside the GPU driver, or the graphics driver. I don't know how well you can see it, but the purple there are all the surfaces that are being operated on by the driver and how long it's taking to work on each surface. And then as you go further down, you look at the different stages, so the binning and the render, resolve, and unresolve and blit stages, and how long it's taking to operate on each of those. So over time, we'll be adding more and more of these elements where you can understand more about what's happening across the entire system on the chipset, in addition to what's happening within Android through the Android systrace data. And finally, anybody familiar with the Adreno Profiler? I don't know how many graphics people we have here. So the Adreno Profiler is the GPU profiler, and we took one of its big features called Scrubber, which is basically a frame capture type mode, and brought it into Snapdragon Profiler. And so what you're looking at is a single frame capture of this particular demo that we had made. And in the middle section in the bottom is a list of all the draw calls that went into rendering that frame. On the top right are all the resources, so your textures and shaders and buffer data. You can view all of that. And one of the features that we also added is pixel history, which is shown in the top left. So I can double click a pixel and see what draw calls affected that particular pixel. All right, so I'm going to shift gears a little bit and talk a little bit about the user experience. And then I'll show you the Snapdragon Profiler stuff as well. So when we typically think about the user experience, what I notice is that a lot of people think in terms of, well, what's that experience that game is giving me or that app is giving me? And we might, Unity developers might be interested in, I want a smooth frame rate or want a responsive UI, want good audio, stunning effects. I want it to be a good gameplay type experience. And all that stuff's very important, but there's a thing called the device user experience as well. They're not, when somebody's playing your game, they're also holding that device. And the factors that might affect the device user experience are going to be the device temperature and the battery performance. Nobody wants to play a game and lose 50% of their battery for over a 10-minute period. Nobody wants to get a 150-degree device in their hand. But the things that you do to affect the game and app user experience can actually affect those things as well. And they're pretty correlated. So if you affect the temperature, you're probably affecting the battery performance and vice versa. But what a lot of people may not realize is if you affect those things too much, it's actually going to affect the things that you care about, your game and app user experience as well. But completely, we're talking about the total user experience. And the point, if you take away anything from this talk, is thinking more about the bigger picture total user experience, not just your app experience or the device experience, but what is the total experience that I'm contributing to for the end user? Because ultimately, that's going to affect your app store ratings. If your app is killing the device or increasing the temperature, you're going to end up getting worse reviews over time. So to give you an example of this is a real-world example. Screenshot from the Snapdragon Profiler, the RealTime. And this application had been running, I think, for 5 minutes. And the temperature of the device had jumped up to 65 degrees Celsius. It was pretty hot. The CPU frequencies had actually been pretty maxed out for the entire time. The utilization was mostly okay. The GPU utilization was pretty normal, relatively high. Can't remember exactly what it was at. And one thing to really quickly note, the battery power is actually inverted on this because it was connected through USB. Ideally, when you're doing battery power profiling, you want to use it over Wi-Fi. So what does the system say? I'm really hot. I'm going to be melting. We need to do something about it. And so it does. It says we got to cool down really fast. And a couple things happen here. Starting at the top, the CPU frequencies drop. These CPU frequencies actually drop to around 300 megahertz. So yeah, it's a quad-core device, but nobody wants to be running their game at 300 megahertz. The next thing that happened was the GPU utilization dropped. So it said, nope, can't use the GPU anymore. We need to cool down. And you can see the correlation with the battery power. Like I mentioned, it's inverse, so it actually went up. But that just means that we're not using as much battery as we were before. All this lasted for an entire minute. So if you're playing a game, and a lot of mobile games tend to be shorter durations, and I'm going to cool down and have worse performance for an entire minute, it's not really the kind of user experience I want to have. It lasted until it got to around stabilized, and you can see the line was pretty stabilized. It's around 55 degrees Celsius, which still isn't necessarily cool, but it's something that the temperature can operate, or that the device can operate at. And once it hit that point, it's kind of saying, okay, we're back to normal. Let's give it a go again. And you can see that all the frequencies kick back in. And of course, the device temperature increases as well. But the GPU is back on, and we start to suck away more power from the battery. The problem is you do this, and like I said, your app store ratings are going to drop. This isn't the kind of user experience that you want to have. So show a little bit about Snapdragon Profiler. I have an actual example here of an application that demonstrates some of the impact of the CPU with Unity on power. And let's see, connected. So I've connected to this Nexus 6. This Nexus 6 is running the Android M preview, developer preview. That's available right now on Google. And the app's not running. Nothing's happening on the device besides the profiler. And I'll go ahead and add a few metrics. So you can see as soon as I add them, the metrics are running. And I'm just going to arrange things so they're a little easier to see, putting all the utilization and frequency metrics on the same graph. I'll zoom out a little bit because the data will be a little easier to see. So I'm also going to add GPU utilization. I'll add that battery power, add that battery power metric, if it'll let me. And then I'll add the device temperature. So nothing is happening. It's very boring. You can see that the CPUs aren't really being utilized. The frequencies are clocking in at around 300 megahertz. Occasional spikes, but that's probably a background service or something running. And battery power is relatively consistent. So you can see something definitely happened right here. But this is actually a great example. I love it when this happens during demos, because here, your utilization, something was definitely executing in the background because nothing's on the screen right now. The frequency spiked, your battery power dropped because we're sucking more battery power, and your temperature went up. Let's see, 32 to 33. So not a lot, 1 degree Celsius, but you can at least see the correlation. So I'll go ahead and kick off the application. And here it goes loading. You can see all the activity. And here I'll select the application. You can see that the metrics popped up here. I'll add the CPU and FPS. And once it actually gets loaded, the FPS will show. Let's move this log cat out of the way. And make the FPS a little more visible. Okay, so the application is running, and I know it's small, but just to kind of show, the application is running here. It's running very poorly, purposely, for demo. I think it's running at 4 or 5 frames per second on here, which looks to be true. Now you'll see these kind of ranges here where it goes up. That's just part of the application. The scene's changing a little bit. And you can see that the temperature did go up. I think it was at 33 before it started. Now it's hovering in that 51, 52 range. We don't have time, but if I sit here and just let this run at this performance, temperature will continue to climb over time. Everything else looks relatively normal. We expect it to be used. I'm going to put it into optimized mode, and you'll immediately see the drop in the utilization and the frequency, and you'll see the temperature start to trickle down. One small point, I was kind of testing this earlier and set the device on a really cold floor. If you're doing temperature measurements, definitely don't do that because the device never warms up. But you'll see as I scale out here that the temperature does drop over time. This is around the time that I switched over. You can see that the utilization dropped, the frequency dropped, and the CPU utilization of the application is roughly the same, and battery power is roughly the same, but the temperature will continue to drop just a little bit, and it's mainly because that frequency, we're not maxing out the CPU frequencies as much. So what does this thing do that causes this? In unoptimized mode, it's actually particle systems in Unity. Just throw in the default Unity settings out there. And I think we were trying to increase the particle amount and just found a threshold where it was just killing the performance. And I guess I did forget to mention the FPS did jump up. I mean, it's pretty variable, but it is running at a much smoother frame rate now. It was down here in that 3 to 5 range, and now it's roughly 30 plus, with a lot of variability, but that's for other reasons. But anyway, the particle system in unoptimized mode is just putting tons of particles out there and has no LOD scheme associated with it. So if you just go out there, put all your particle systems out there and have no intelligence about when those particles are actually running, that's just going to be more CPU work that needs to be done, which on mobile devices is going to mean higher CPU frequency, which is going to mean more power draw and higher device temperature over time. And it's a very small thing. You wouldn't think that it would necessarily be a problem, but it's something on mobile devices at least that you have to consider. So some other things to show. I had mentioned the trace, so I'll skip over to the trace mode, and I'm going to do something I probably shouldn't do. I'm going to show you a broken feature. But it's because I just want to show you something that we do have. It's broken on this particular device. This particular device I found out did not have the driver update that we needed. So the timeline correlation is going to be wrong, but what I've just done is this trace section is all your Android systrace categories. So you can select which ones you want. And then I selected the process, the application that's running, and when I selected that, this GPU stages metric came up. It's a graphics application, so I can poke in and find out the stage timing of each of those, or what's happening within the driver. So I'll start a capture, stop a capture, and we start to get our data. So just to show you the messed up part, this section down here should be correlated with all this other data from systrace, but I want to show you just so you can see kind of what's coming. We did just release this tool. There's definitely some problems with it. But I select this surface, and I can see the surface. I can see the pointer of the surface, so I can drill into my code and figure out which one it is. I can see all of its attributes, and then I can come into the binning that it took. I can see how long it took, the render pass, or the render stage, how long that took, and the resolve. And something of interest is here we have a bunch of unresolves, all these yellows, and these unresolves are actually caused by the default Unity blur shader. That was one of the other things we found out while developing this little demo app is you don't want unresolves, for sure, by the way. But you might want to optimize the default Unity shader for blur because it actually has an impact on your power and GPU performance. Just to zoom back out. Where's my systrace? There it is. Like I mentioned, all the systrace data. Here's your CPU scheduling. And you can start to see some of the colors. So here's your Unity process, and I can actually make that a little easier to see. Typically with a CPU-bound application, you would see a lot of threads in the CPU scheduling on Android systrace. And since this application is actually running more optimized now, it's a bit better. But in the unoptimized mode, there's quite a bit more blocks going on here. We plan to add a lot more features to this to make it easier to understand what's going on with your threads, but typically from an optimization standpoint, you don't want to see the scheduler sending your threads to different cores. You want to try to keep your threads on the same core as much as possible. The last thing is Snapshot, and here selecting Snapshot capture changes the complete view. And let me make sure this is running. So all I need to do is select my process, and at this point I can select any metrics that I want to select. I'll select the GPU clock so I can understand how many clocks is every draw call taking. I'll go ahead and kick off the snapshot. Now this takes a little bit of time. The more complex or resource intensive your application, the longer it's going to take. But it captures all the data. Here's my pretty application. Captures all the data, transfers all the data, and we can start to poke at it now. So here in the main screen, we get our screenshot. And I've increased this section here, which is all the draw calls. And for every draw call, I can poke in and see what are the API calls that went into that draw call. And I can also click on a draw call. And what this does is sends command back to the device. We do all the processing on the device, mainly so that you can understand what's happening with the particular driver version that you have. Because different devices are going to give you different results. But you can see the flashing of that car. So this draw call is actually drawing this car. Over here, I can click this little filter here, and it'll show me which textures are being used for this draw call, which programs. I can look at the buffer data. But here I can select the program and actually look at the source code for it. So here I have the vertex shader, quite a bit of code, and flip over to the fragment shader. And looks like I selected a particularly not so simple one. So what I'd love to show you is modifying the shader and uploading it back to the device, but maybe I should have planned better. But here I can see all the draw calls. And one thing too is you don't want a lot of draw calls. In the unoptimized version of this app, that's when I do the unoptimized CPU version, there's 150 plus draw calls, and that's mainly because of all the particles that are being rendered. But by just making that simple change, we have a lot less draw calls. Let me go ahead and get back to the default frame state. There we go. Okay. So last thing would be pixel history. So I'm going to double click that pixel, and here we send the command back. We'll do all the processing on the device, and in a minute we'll get, or hopefully less than a minute, but very soon we'll have our pixel history showing which draw calls affected that pixel. Okay, so down up here in the top left, I can see that draw call 14, 15, 16, 60, and so on. So quite a few draw calls are hitting this pixel. I got a few depth test fails. But from here, I can start to dig in and find out what exactly is happening during these draw calls, how they may be affecting performance, and so on. One thing I did forget to mention on the shaders too is down here we have the shader statistics. And as I actually type, you can see the net result of the compiler. So I guess maybe, no, that was not going to work. Anybody remember what that was? There we go. You can actually see the net results of the shader statistics. So as you optimize your shaders, you can see, am I taking less instructions, more instructions, and so on. So I think we're getting close on time. Yep, 1 minute. But I can open up to any questions. I know we have a break as well, so I can stay a little longer if needed. Let me throw a quick summary slide up. Always got to close. Really quick summary. The one key point I really wanted to push today is that you got to think about the total user experience, the app experience, plus the device experience. You're going to get happier users that way. Small, simple changes can really affect the performance and power consumption. Visit developer.qualcomm.com if you want to check out these tools. We also have a booth, and we can definitely give you a more in-depth demo about this and talk more about power and thermal performance. So, any questions?
The temperature, is that calculated or measured from the device?
It's measured from the device.
Okay. I got more. So if I want an app at 60 frames a second, I'm going to get 16 milliseconds to do stuff, but that's going to peg the CPU. To be, I guess, better with temperature and power, what am I actually looking at as far as how much time I get to run in a frame?
The interesting thing is the higher FPS you can get, generally the better, because you're using the CPU less, provided you don't become GPU bound. So okay. I know it sounds kind of odd, but if you want to just minimize the amount of time you're spending on the CPU. In fact, if you can use the GPU more, you will actually get better power and thermal performance.
Okay. One more. If I'm a dev and I'm testing out the temperature, I'm holding it in my hand in an AC'd office, what is the delta between that and what a guy on a subway will probably look like? Is it even that much different?
So probably one of the reasons we didn't see much variability in the temperature when I went to optimized is because it's sitting here on the table and I got a nice cool breeze coming right here. But if I was holding this in my hand, just the act of holding in my hand increases it probably 3 to 5 degrees Celsius. So I think if you want real world use case, you probably want somebody to actually hold the device because it is going to have an impact. And there's kind of a loop-back feedback system there between your body temperature and the device temperature, okay, kind of increasing together.
Is that as strong as the difference between like holding it in a 72-degree room versus an 80-degree outside world, or is hand really the demanding factor there?
I've never tested outside.
Okay.
And San Diego weather is like 72 degrees, so.
Thanks.
But yeah, I would think so.
So I also have 2 questions.
Sure.
So does the Snapdragon Profiler contain any information about queuing behavior, like GPU view might, for example?
Queuing in what way?
For example, in GPU view, I can say which packets have dependencies on it, but essentially like the order in which they're submitted and what's waiting on what.
Okay. Yeah, not yet.
Okay.
We don't have that yet.
Okay. And it obviously doesn't support like Exynos or anything, does it?
Correct.
Okay.
The question is, what was the simple fix that we made for the demo, right? It had to do with the particle systems, and it was really two things. One was having more of an LOD scheme for the particles. So if it was far enough out that at best you might get a couple pixels worth of particles, then we don't even render it until it becomes more obvious. And the other was just having a better emitter rate, so we weren't putting more particles out there than we needed. Yeah. They're independent. I mean, they're correlated because, you know, the system might take over, kind of like that screenshot I showed. The system might take over and just collapse your frequencies because it needs to cool down. But they're independent values that we read. So you might be using a lot of battery power, but your temperature may or may not necessarily rise. Typically, you're going to see a lot of correlation between the two, though. That answer your question? Yeah.
So it's higher. I mean, how you measure you measure the total power consumption, or the actual you're tapping on the battery voltage level.
Yeah. The question is, how are you measuring the battery power, the battery consumption? So we're reading that information out of the hardware. And I believe, and maybe Rick can.
There's a power management IC, so we read it directly from the power management IC, read the current, and then we use battery voltage to get the power. But there's no direct correlation between the battery voltage and the power.
Yeah, so for everybody else, we have what's called the power management IC, and that's where we read the power values from. And there's battery current and battery power measurements, and voltage measurements that we get from there. Any other questions?